Hello, this session is about logarithms, specifically about the laws of logarithms and solving logarithmic and exponential equations. Going into this video, there are a few things you should probably already know about logs, and those include these kinds of things. Number one, remember that a logarithm is kind of like a question function. For example, another question function might be a radical. If I asked you what the square root of 16 is, what you're asking yourself is, what squared is equal to 16? And the answer to that question is 4, and so you'd have the square root of 16 equal to 4. When I ask you what log base 2 of 8 is, what I'm really asking you is 2 to the what power is equal to 8. Well, 2 to the third power is equal to 8, and so your answer is 3. Likewise, log base 2 of 2, 2 to the what power is 2, would be 1, giving us the rule that log base anything of itself is going to be 1. In addition, log base 2 of 1, 2 to the what power is 1? Well, 0 is the only exponent that always ends in 1, and so log base anything of 1 should be 0. All right, so let's go ahead and let's begin looking at the laws of logarithms. On your calculator, you'll notice that you only have 2 logarithmic buttons on your calculator. One is the natural log button, and the other is the log button. Now these logs are asking you for delivering to you very specific base information. Natural log of x is log base e of x. So anytime you type natural log of a number in your calculator, what you're really asking for is log base e. Log of x is actually log base 10 of x. So that is what's known as the common log. This ln, of course, is called the natural log. It's called the natural log because e is a constant that's commonly used in exponential functions and crops up quite often. You can study the history of e, where it came from, all of those kinds of things, by doing a little bit of research. We're not going to do that here because this is not the place for that, but it is interesting information. I encourage you to go look that up if you're curious. All right, so moving on to the laws of logs. Because in your calculator you only have natural log and the common log, there are going to be times when you cannot calculate a logarithm simply through logic. For example, if I asked you what log base 2 of 9 is, well, I know log base 2 of 8 is 3, and I know log base 2 of 16 is 4, so it's probably somewhere between 3 and 4, but in order to get an exact number, I need to do something to be able to have the calculator calculate this for me. And the way that I do that is this. If I have log base A of B, the change of base formula, the change of base rule, if you will, allows me to change the base of 2 logarithms and find a quotient. So if I used, let's say I used natural log, I could use the natural log of b over the natural log of a, and that would give me the correct answer. That would give me the answer that I seek. I could also use the common log of b over the common log of a. Indeed, I could use any log that is common to both the numerator and the denominator to figure out what that value is. So in the calculator, I would want to put in log of 9 divided by log of 2 to find this answer. Now, an interesting piece of information is that if I want log of 9 divided by log of 2, the calculator is going to automatically open these parentheses for me, which means I have to close them before I divide, which means it opens these, so I'm going to close them before I hit enter. Okay? Just a little piece of information there. All right, let's talk about some of the other laws of logs. There's 3 more, and these 3 work in conjunction with each other, and you'll find that they're very helpful in, there's usually a piece of your logarithmic homework that's going to be condensing and expanding logarithms, and this is where this comes in very handy. Multiplication and addition of logarithms works like this. If I have, and they're very connected to exponential rules, and this helps me remember them. I know that if I have like bases, and I am multiplying them together with different exponents, what do I do with the exponents? Well, then I'd still have the same base, but I'd add the exponents, right? So a to the b times a to the c is a to the b plus c. So that's a rule that we know. It's a very common rule. We can link that to the logarithmic rule that goes like this. The log base c, all right, of a times b is the same thing as log base c of a plus log base c of b. So this multiplication inside the exponential yields addition, inside the logarithm, yields addition outside it. Just like multiplication yields addition here, multiplication yields addition here. Okay, so it can go back and forth. So what kind of rule do you think is going to happen with division and subtraction? Well, let's again go back to the exponentials. A to the b over a to the c is a to the b minus c. You subtract exponents in this position. So what do you think would happen with log base c of a over b? Well, you're going to end up with log base c of a minus log base c of b. Now notice that these bases continue to be the same. You have to have the same bases when you're condensing and expanding. Just like this base didn't change when I went here, these bases don't change when I subtract those exponents. The bases on the logarithms won't change either. And the last one, exponential and coefficient. Now this one is linked a little bit more loosely. It's not as obvious a connection if you don't have just a little bit more mathematical knowledge than you may have right now, and that's okay. If I had a to the b and I raised all of that to the c, what do I do with my exponents? I multiply them. So I get a to the b times c. So let's talk about what would happen with a logarithm that looks like this. Okay, log base a of b to the c is c times log base a of b. So exponential is going to yield multiplication, but maybe not in the way you expected it to. You would expect this maybe to be log base a of b times c, but that's not the case. So that exponent becomes a coefficient when we do the expansion on this one. This is considered the expanded version of that. Okay, so and one other piece of information is that this is not the same. Let's just write it out this way. Log base a of b to the c is not the same as log base a of b raised to the c. It's very, very much not the same thing. So please be on the lookout for that. In a math book or a online homework or whatever you're looking at, more than likely, if they write it this way, they mean this. Okay, they probably do not mean this. Most math texts are going to be very specific about putting parentheses around that logarithmic expression if the exponent is to be applied to the entire thing. So don't worry about that, but do know that there's a difference. All right, so let's move on and let's talk a little bit about, or let's practice a little bit with the expanding and the condensing. Notice that all of this in here is inside this logarithm, log base 2 of x to the 4th y square root of z. Because they're all multiplied together inside that logarithm, we can expand them through addition. So remember that multiplication expands into addition. So we're going to say log base 2, keeping the same base on our logarithm, and log base 2 of y, and log base 2 of rad z. Now we have some exponents here. We have an exponent here that's pretty obvious, so we can take our exponents and turn them into coefficients. Okay, so we can say this is 4 times log base 2 of x to the 4th. And there is no exponent here, log base 2 of y. But here, check this out. Don't let this go past you. This guy here is the same thing as saying z to the 1/2. And if that's not something that occurs to you immediately, you probably should practice that because that one's going to come up quite often. So we're going to end up with 1/2 log base 2 of z. All right, and that is the expanded form. There's nothing else I can do with that. It is not, oh, whoops, this is not correct. Pardon me. Hopefully you already caught that and said, oh, Melody, you're wrong. But there is no exponent here because I pulled it down to the coefficient. I apologize. There's nothing else that I can do with this, though. This is it. It's not an attractive answer, but it is indeed the answer. All right, let's go to condensing. Now, we're just going to do what we just did in opposite order. So I'm going to take my, my coefficients, and I'm going to pull them up and make them exponents. I'm going to say this is log, keep the base, to the third, log, base 4 of b to the 1/2, log, base 4 of c to the 12th. Okay. Now I can condense this, and I know that subtraction is paired up with which one? It's paired up with division, addition with multiplication. So watch what happens. There's kind of a fun little shortcut step here. So I'm going to say this is log base 4. This all goes in at the same time. And now we're going to end up with a fraction. And the reason we're going to end up with a fraction is because of this division here. That's going to give me the fraction. So I've got a to the third on the top, because it's positive, b to the 1/2 on the bottom, because it's negative, and c to the 12th on the top as well. We can rewrite that using radical notation, a to the third, c to the 12th over rad b, because we know that b to the 1/2 is the same thing as the square root of b. All right, so I encourage you to go back over these a couple of times. Make sure that you understand them before you attack any homework or whatever you're prepping for. All right, so let's see what we can do with this information. Who cares about the laws of logs, and what are they good for? So let's do a little exploring here. A to the x plus 5 is 60. When I solve exponential or logarithmic equations, either one, the goal is the same. My goal for solving an equation is always to isolate the variable. And we do that in different ways depending upon the operation. If I've added in the equation, then I'm going to subtract. If I've multiplied, I'm going to divide. If I've taken the square root, I'm going to square it. You know, whatever. The same thing is true. So finding the variable, isolating the variable, those rules don't change. I'm just going to use inverse operations until I have isolated the variable. The first inverse operation would be subtraction. Get rid of this 5. And I get e to the x is equal to 55. The next operation that I need to undo is this e to the x. E to the x is an exponential. And the inverse of an exponential is a logarithm. And that is very important to keep in mind because it's going to come up over and over again. So the inverse of this particular exponential is log base e. So to get rid of e to the x, I need to use log base e. My laws of logs tell me that I can take x and make it the coefficient because it is currently the exponent. And I know that log base e of e is 1 from that first screen. So x is equal to log base e of 55, which we also know to be the natural log of 55. You can put that in your calculator and you've got it. Okay, so let's go on and let's look at another example. Okay, now this one is not as obvious. This one's a little bit trickier, and I want to show you how to look for this. And I think it's worth doing because it shows up in not just the logarithmic and exponential kinds of equations, but it's also going to show up in trigonometric equations. It shows up in calculus equations and other things later on in your math career. So if this is something that you're going to continue to do, if math is something you're going to continue to pursue, then you're going to want to be able to identify these kinds of things. suppose, okay, so I'm looking at this, and the first thing I look at is e to the 2x minus 3 times e to the x plus 2. I have like bases, but I don't have like exponents, so I can't combine like terms. There are no like terms. So there's not going to be any really simple, subtract 2, divide by 3, take the natural log, and I'm done. That's not going to work here. So instead, what I want to do is I want to identify the fact that this is quadratic. Suppose I let a be e to the x. Then I can rewrite this as a squared minus 3 times a plus 2 is 0. And that is so clearly quadratic. And so I can use the quadratic formula, I can complete the square, I can factor, whatever makes me happy. Personally, it makes me happy to factor. So I'm going to factor this out, a minus 2, a minus 1, okay, which means that a is 2 or a is 1. I put my e to the x back in because if I start with e to the x, I got to end with e to the x. More specifically, if I begin with x's, I need to end with x's. Okay, and so now I've got the same problem as I had up here. So this is the same kind of problem. So all I have to do now is to take the natural log of both sides on both of these equations. So natural log, natural log, natural log. And I end up with x is equal to natural log of 2. And x is equal to, now what is the natural log of 1? Remember, log base e of 1, or log base anything of 1, is 0. So we end up with x is equal to whatever the natural log of 2 is. You can put it in your calculator, or 0. Okay. By and large, there are a lot of math teachers who are more interested in seeing you put down an exact answer than an approximate answer. And when you put natural log of 2 in your calculator, you're going to get a decimal, and it's not going to be a rational number, and you're going to have to round it. And that's called an approximate answer. It's not an exact answer. Natural log of 2, on the other hand, is an exact answer. So depending on your teacher, you may find that this is a more acceptable answer than whatever decimal that is. All right. So let's go to logarithmic equations. What happens if we've got logarithms? So the same kind of first rules apply. I'm going to subtract 2 from both sides. I'm going to divide both sides by 2. And I'm going to say to myself, okay, natural log of x is the same thing as log base e of x equals 1. So what is the inverse of log base e? Well, it's raising both sides from e. E raised to the log base e of x, e raised to the 1. Okay, so what that gives me is e to the log base e. Those are going to cancel out and leave me with just x. And then e to the 1 is simply e. Okay, again, e is an exact answer. You could put down 2.718 or whatever it is, but it's that's an approximation. So e is a more exact answer, like pi. Okay, let's look at this guy. Here's where our condensing rules come in really handy. This addition of 2 common logs means that I can condense the left-hand side of this equation before I even begin to solve. I can say that this is log of, and addition yields multiplication. Okay, since this is a common log, since I know that log of 5x times x minus 1, this is a common log, I can raise both sides from 10. And that gives me, and I'm going to go ahead and just multiply this out, minus 5x equals, and then 10 squared is 100. Now, it's very important to do the right side of the equation. I can't tell you how many student papers I've seen with the right side of the equation. They just kind of forget it's there, and then all of a sudden it's still 2, and then it won't factor, and all kinds of crazy things happen. So if I divide everything by 5, and then I move everything over to the left-hand side, I very clearly have another quadratic. So I have x minus 5, x plus 4, and look what happens here. I have x equal 5 and x equal negative 4. Now, there's a problem with this, and I didn't discuss it on the very first equation that we did with logarithms, and I probably should have. But when you have a logarithmic when you have a logarithmic equation, you have to be careful of your answers. Because while an exponential, e to the x, 3 to the x, whatever, those are not limited. The domain is all real numbers for an exponential. For a logarithm, however, the domain is not all real numbers. For y equals log of x, the domain is that x has to be greater than 0. You can't put in 0 and you can't put in a negative. You can only put in positive numbers. And so you have to be careful about what answers you get. Notice that if I put in 5 into my original equation, I get log of 5 times 5, which is 25, plus log of 5 minus 1, which is 4. And those are all positive numbers. That's cool. So this one shouldn't have a problem. But log of negative 4, okay, log of 5 times negative 4 is log of negative 20. You cannot calculate the log of a negative number. This one doesn't work. And so my only answer is x equals 5. So be sure to check your answers when you're doing logarithmic equations. Okay, so that's going to finish us up for logarithms. Hopefully this has been helpful to you. If you have any questions about what I have covered today, feel free to drop me a line. You can visit me at melodyelrod.com and drop me an email that way, or you can send me a message through YouTube, either one, and I'd be happy to give you some extra help. Feel free to check out my other videos as well, and hopefully one of them will be helpful to you. Have a great day.